Welcome everybody to our colloquium today. It is my great pleasure and honor to introduce Professor Ash Clerk from University of Chicago. Ash is a theoretical physicist. His work spans few different areas, including condensed matter physics, quantum optics, and quantum information, with deep expertise in driven dissipative quantum systems, I'd say, and Ash is a professor of molecular engineering at the University of Chicago. He did his bachelor's at the University of Toronto, and I learned recently that he started his journey in quantum optics during his bachelor's, working on a project at that time. He did his PhD in physics from Cornell, where he worked on condensed matter theory, I believe quantum physics, if
among other things.
Among other things, right. He was then a postdoc at Yale, where he worked on a number of amazing topics, including quantum measurement and noise. If you want to go to a definitive reference on quantum measurement, I would highly recommend Ash's Review of Modern Physics article on the topic. He also did several important and seminal works in the field of optomechanics and circuit QED. And he was then a professor of physics and Tier 1 research chair at McGill University until 2018, when he moved. 2018, is that right? 2017.
Close enough.
Sorry.
Long time ago.
2017, when he moved to University of Chicago. And Ash's work has been recognized through several awards, including the Simons Foundation Investigator Award and the Rutherford Medal in Physics from the Royal Society of Canada. So it's my great pleasure to welcome Ash, and please, looking forward to your talk.
Thank you very much for a very kind introduction, and also for the invitation to come here. I think I passed through Tucson once, maybe 12 years ago. I think Pierre Maestre had organized a really nice school that I lectured at the Biosphere. So I passed through, I never got to stay. So I'm glad to make up for that 12 years after the fact. Okay, so the work I'm gonna tell you about today, harnessing dissipation and noise for quantum sensing. One of the directions my group, a theoretical physics group, is really excited about is this topic of quantum metrology and sensing. Can we use quantum resources like entanglement, like squeezing, to have new powerful ways to learn about the physical world? Okay, and the story I want to tell you is to tell you a story where something that seems like it should obviously be a very, very bad thing can actually be a good thing if you use it the right way. So the thing that we would think is obviously bad if we're trying to do something quantum is dissipation and noise. And we would think we should do everything in our power to kind of avoid it. I'm going to tell you that's not the only strategy to employ. If you can control the dissipation and noise, well, then that gives you an incredibly powerful resource. In some ways, you can do things you could never do if you just try to take a noise-free strategy. Also, I'll try to convince you that thinking about this problem of quantum sensing, using dissipation to do good, it's not just a bunch of practical tricks, so that practical tricks are interesting and important. It's also a great way to learn new things about quantum physics. In particular, the structure of many-body entangled states, the complex dynamics we have in dissipative quantum systems. Okay, so I know this is an optics colloquium, right? And a lot of my talk is going to be about systems of many qubits. Okay, so to avoid any extreme disappointment, the tact I'm going to take is, even though I want to tell you about many-body qubit systems, which can be great sensors, I'm going to make a connection to a piece of quantum optics that I'm sure many of you know about. I'm going to tell you about how, in some ways, the simple, beautiful physics of a single mode squeeze state can actually give us a great template to think about all sorts of more complicated entangled states. Okay, so that's the plan. I'm happy to take questions as it goes along. Let's get started. So again, it's a colloquium. Let me start with a really big picture motivation. One of the motivations is, can we do something useful, right, with some of the more counterintuitive aspects of quantum physics? Unless you've been living under a rock for the last 10 years, and maybe even if you have been living under a rock, you know this is a topic that has the interest of government, of industry, and certainly academic researchers. So this idea, this kind of quest to build quantum technologies, we often think about three very general categories. It's this one, quantum computing, that tends to get all the attention and all the press. What I want to tell you about is this thing in the middle, right? This idea of using truly quantum resources to make it easier to make measurements, to sense things, to learn about the physical world. Okay, so you've taken your first quantum mechanics class and someone tells you, oh wow, quantum mechanics is great for measurement. Quantum mechanics will let us build great sensors. You'll be like, this sounds like complete nonsense. If there's one thing you remember from your first quantum mechanics class, it's the uncertainty principle. That's something that does not seem very good for making sensitive measurements in the quantum world, right? So what are some of the consequences of the uncertainty principle that hinder measurements? We know that there's the idea of intrinsic quantum noise, vacuum fluctuations. So this blob here is supposed to be a probability distribution describing a single mode of light. So x1 and x2 would be quadrature amplitudes. So the amplitudes of the cosine and the sine components of that field. And this probability distribution, this is representing a coherent state. It is not just a dot, right? That thing has to have a width. That's the intrinsic quantum noise. This is just a displaced ground state of a harmonic oscillator. That's a direct consequence of the uncertainty principle. That's a problem for making measurements, right? If you're going to use the light to probe something, that kind of intrinsic fuzziness, that seems like a bad thing, right? Another consequence of the uncertainty principle, kind of reinterpreting the quantities here on the left-hand side, is the idea of measurement back action. So this is a little cartoon depicting the physics of the Heisenberg microscope. I try to measure the position of this red particle by shining light on it, bouncing a photon off of it, right? To make a sensitive measurement, I need to make the wavelength associated with that photon shorter and shorter. But in doing so, the random momentum kick I get in that scattering is going to be bigger and bigger, right? So we also have this idea of back action, right? That is intrinsically a part of quantum measurements. That's bad. When you're trying to measure something, the fact that you kick it around, this is generally not a good thing. Again, something that seems to be bad news for quantum mechanics and measurements. A last topic that maybe is a little less familiar, but no less important and something dear to my heart is amplifiers are super important to make practical measurements, right? So here's my theorist depiction of an amplifier. I send in some signal, it's got an amplitude. I want it to come out, that's this propagating wave packet, bigger. Quantum mechanics tells me I can't do that perfectly, right? There has to be some added noise there. Okay, so at first glance, if you've taken Quantum Mechanics 101, quantum mechanics seems to be bad for measurements, right? But then you take your second quantum mechanics class and you learn, well, look, there's some other features of quantum physics that maybe can actually help us in our quest to learn about the physical world. Okay, so in the middle here is a cartoon showing the basic idea of squeezing. So look, the uncertainty principle tells me I have this probability blob describing my single mode of light, but the uncertainty principle doesn't tell me what the shape of that blob has to be. So maybe I can play tricks to shape that circular blob, just the ground state uncertainty, into this kind of ellipse. And now at least I have one direction in phase space that's very narrow. Maybe I can harness that for kind of sensing in a more efficient way. Okay, so that's the idea of squeezing. On the left here is supposed to be just a very generic depiction of an entangled state of a bunch of qubits or spins. This is a GHZ type state. So these kinds of entangled states, the right kind of entanglement, can be a useful thing for sensing, and I'll tell you more about that. And on the right here is something that actually combines both of these examples. So what is this? This sort of looks like squeezing, right? I've taken some circular probability distribution, squished it, right? But now this probability distribution lives on the surface of a sphere. Okay, so this is actually a cartoon I'll unpack a little bit more. This is the basic notion of spin squeezing. So this is an idea that I can combine both of these things together. I can take a system of many, many qubits, entangle them the right way, such that I reduce fluctuations in some collective quantity of those spins. Okay, so these are some basic resources, new resources that quantum physics gives us that we'd like to exploit for sensing, right? There are already, maybe not a ton of examples where these quantum resources have done something good, right? Probably the biggest by any scale, whether it's distance or mass or sheer number of New York Times articles, example of quantum resources doing something good is this beautiful use of squeezed light in LIGO, right? The world's biggest Michelson interferometer, this sort of detector of gravitational waves. They have successfully used the right kind of squeezed light to improve their sensitivity. Okay, so this is not a LIGO talk, so I'll give you a 30-second depiction. You're looking at a very, very large Michelson interferometer. Gravitational wave comes in, it gives you a differential change in these two path lengths. That's what you're going to detect at the output port. You're shining light into this thing to make your measurements. The quantum noise in that light, that same, fuzziness that I had here, that's going to be a problem for your measurements. At high frequencies, it's going to limit your ability to resolve a small phase shift. At low frequencies, it's going to kick around these mirrors, that back action I told you about, and that is going to limit you. Okay, so to use squeezing, right, make the light going into this interferometer a little bit quantum, you've got to do it the right way, because the way quantum mechanics messes up your measurements, it's different at low frequencies and different at high frequencies. And the beautiful thing they were able to do in LIGO is basically devise a way of doing frequency-dependent squeezing. So the way the light is squeezed, squished, depends on the frequency you're looking at. Long story made short, this is basically the sensitivity or the total noise of LIGO as a function of frequency. So we're going down to 30 hertz to, 3 kilohertz. Black is with no squeezing. Purple is with this kind of optimized squeezing. Okay, so just an example that these kind of quantum tricks I'm going to tell you about at a very theoretical level going forward. They're not easy to use in experiments, but there are, again, more than a proof of principle experiment. This improvement in the noise floor at high frequencies of, something like 6 dB, this is a huge win in terms of the overall sensitivity of LIGO. Okay, so having convinced you that quantum sensing is something we should all be thinking about, and look, if it works for LIGO, it should work for other things. What is the kind of question that I want to address? Well, I want to turn attention to maybe not thinking about states of light, but using sensors that are really collections of qubits or collections of spins. And I'd like to squeeze them, whatever that means, or put them in some entangled state that could be useful for sensing. And what's the standard way to generate entanglement? Well, entanglement means the spins, the qubits have to be correlated. How do I correlate a bunch of initially uncorrelated objects? I have them interact. Okay, so if these were like two-level atoms, maybe I stick them inside a cavity, right? The spins or atoms are detuned from the cavity light. I have photon-mediated interactions between the qubits. I basically generate some interaction Hamiltonian. This is the Hamiltonian. And the idea is that hopefully if I get that Hamiltonian right, it will take some product state, qubits not entangled at all, and give me this magical entangled state that's useful. Okay, so in this paradigm, the idea is you want some good entangled state for sensing. You have to design the right Hamiltonian. You have to generate the perfect unitary dynamics that does what you want. And in this picture, of course, noise and dissipation are terrible, right? Noise and dissipation, so here dissipation is I've got my qubits in some perfect quantum state. Maybe energy is leaking out. I have T1 decay. Maybe there's noise coming in. I have some dephasing of the qubits. This is all terrible. It's going to disrupt this dynamics. It's going to prevent the formation of an interesting quantum state. Okay, so the normal strategy is try to realize this sort of, cartoon dynamics. Do everything in your power to minimize noise and dissipation. So in the standard way of doing things, we would love to have the two-level atoms in a cavity that has almost perfectly lossless mirrors. So there's no loss generated by the cavity photons on the spins, right? And again, the whole story I'm going to tell you is that's not the only way to approach things. As opposed to just trying to minimize these ingredients, embrace them, but do it in the right way. Okay? So on this slide, here's just an outline of some cool things you can do using the right kind of dissipation and noise to sort of enhance sensing, right? The main thing I'm going to tell you about is the idea that, okay, for sensing, we need the right kind of entangled states. Maybe I can use dissipation to prepare those entangled states. And I'll try to tell you how you can do that, how that's compatible with real experiments, and why you would want to do that. It's a kind of cool thing to do, but it has practical, advantages over other approaches. If there is time, I will tell you a little bit about some of these other ideas. It's not just the ability to use dissipation to stabilize interesting entangled states. Dissipation gives us different kinds of dynamics. The dynamics is not unitary. It's not described by a Hamiltonian. Information is not conserved. So there are ways of using purely dissipative dynamics to actually read out your quantum system. Okay, and so I'll try to tell you a little bit about using something called superradiant decay as a potentially really powerful way to read out your qubit sensors, right? So big problem is maybe your spins are in this beautiful entangled state. This is all great. They've acquired some information, but now you try to read out those spins and your readout is terrible. And so then normally you'd be like, why are you even thinking about entangling your spins? Fix your damn readout, right? The cool thing with these dynamics is you don't have to do that. This kind of dynamics gives you a kind of amplification. Even though your readout is terrible, you're able to amplify the information in a way that you can still make use of some initial entanglement. Okay, and the last thing that I'm sure I will not have time to tell you about, but is super fun. Again, I was trying to stress even a few slides ago, thinking about these questions, thinking about entanglement and dissipation as a resource for metrology. Yes, hopefully we come up with some practical things that people can use to actually implement and improve quantum sensing experiments. But we also can learn some fundamentally new things about many-body quantum dynamics. So something that we're very interested in is in this cartoon here. If I have a physical system and it's dissipating, right, into some environment here drawn as a waveguide, how do I think about all the information in that waveguide, right? What's the dynamics of that? How much information is there? What happens when I'm near a phase transition? And how do I get the information out of that environment? Okay, so that's where I'd like to go. I think for the colloquium, we'll mostly cover this first box here. Let's kind of dive into things in a bit more detail. Yeah, and please ask questions. Yeah, yeah.
When you said amplification, this is not actual amplification in the gains?
So it's going to be a spin amplification. So the idea is it's not when I think of amplification, I normally think about amplifying a state of light or a state of a microwave field. The amplification is going to be at the level of these qubit spins themselves. So I've got a bunch of qubits, there's some information in them. I want to do something to those qubits that, in a sense, the information is bigger, it's easier to access. Yeah. Yeah, and again, please ask questions if something isn't clear. Okay, so to make things a little bit more precise and not talk about things just at the purely cartoon level, we have to maybe formalize a little bit in terms of what do I mean by quantum sensing and quantum metrology. And there are many, many different ways to think about those topics. I'm going to think about, in a sense, the most basic and most ubiquitous version of quantum metrology, where the task is just to estimate some small parameter that you have a way, and this parameter is classical, no hats on that theta, and you have some way of encoding that parameter in a quantum state. Okay, so this is quantum parameter estimation. The basic procedure is you have some quantum sensor. It's in the simplest case, some pure state psi. You want that state to now depend on this parameter. So you're going to encode the parameter on that state, typically with some unitary. So now you have a state that depends on that unknown parameter theta. Okay, and your goal is you want to know what that theta is, right? So this could be the light going into an interferometer. This could be imprinting a phase right in the middle of the interferometer. This could be the light coming out of the interferometer. So the next step here is you measure something of that state, right? And I'm calling those measurement outcomes Q. And then using those measurement results, you make an estimate of what that parameter is. Okay, so this is the basic paradigm of quantum parameter estimation, right? And let me give you a concrete example involving qubits that is maybe the most ubiquitous form of quantum parameter estimation with spins, right? This is basically a Ramsey-style sensing sequence. So my sensors now are a collection of two-level system spin 1/2 qubits. I'm going to think of this collection of big N qubits as just a giant angular momentum. Okay, so a fully collective state, just think of this big arrow. All the qubits in the simple example are kind of working together. And then what is this Ramsey sensing sequence? And again, this is done, for example, in atomic clocks. All my qubits are described by this big collective vector. I think of them living on this collective block sphere. So what is the sensing sequence? I tilt this vector so that it points in the x direction. So that means all of my qubits are superpositions of sigma z up and sigma z down. And then what is the sensing, right? I basically apply this unitary here, right? So the sensing is this collective vector describing all my qubits gets rotated a tiny small amount, right? So there's some small frequency shift or frequency detuning of these qubits that causes a bit of a rotation of this collective vector, right? And then the idea is, well, the signal that you care about, before you applied this unitary, there was no y component of this vector. Now there's a tiny y component. Okay, so in this Ramsey style, so the state here the way I've drawn it is just some unentangled state of all of my n qubits, right? The preparation here is this unitary where I do a rotation about the z-axis, right? And then the measurement, naively, we'd say, oh, we just measure the y component of all these qubits. Okay, and so then the question, the fundamental question is, how good is my measurement, right? And in particular, the thing we care about is, as you have more and more and more qubits, how does your measurement get better and better and better and better? Okay, so for this Ramsey protocol here, what's the minimum estimation error? This is the thing I'm measuring. I kind of know what the signal is, and it's growing with the number of spins, that's great. But of course, I need to know what the noise is, right? I need to know, okay, that's the average value of SY. What are the fluctuations? Okay, and this is where entanglement can come and help us, right? If there was no entanglement, so if it's like the way I've drawn it here, I just had a product state of all of my spins, then it's easy to show that what is the variance in this quantity that has all the information. I just basically have a contribution independently from each spin. I get some fluctuations that grow as n. Okay, so then if I do a signal to noise ratio, if I square this signal, divide by the noise, take the inverse of that signal to noise ratio, my sensitivity, what's the smallest rotation angle I can sense, that's going to get better is 1 over n, right? So my actual sensitivity, 1 over square root n scaling. This is what we call standard quantum limit scaling. This is what we might even expect classically, right? For repeating something over and over that's not correlated. We want to do better. So how do we do better? I would somehow like to make the noise much, much, much smaller. How do I make the noise much, much, much smaller? Well, here I just added up the independent fluctuations from each qubit. I need to correlate the qubit somehow, right? So when I add up their fluctuations, I get something much smaller than n, right? That is going to be using entanglement. And again, if I wanted to draw the state of my spins now, not just as this classical arrow, but as a probability distribution in terms of where does the arrow point, what I'd like to do is basically squeeze the fluctuations of this spin, right? So because the information is in y, I would like to make this probability distribution really, really narrow in the y direction. So exactly the same way that we think about squeezing of a bosonic field, right? You don't violate the uncertainty principle, you just massage it in a way that is good for you, right? Good for what you're trying to measure. We'd like to do the same thing with spins. Okay, and this idea that, oh, if you have the right kind of entanglement, you can actually improve your sensitivity, your scaling. As you have more and more qubits, how much does your sensitivity improve? The fact that you go from 1 over n to 1 over n squared, this is something very, very general. Okay, and so maybe for, not to go through this in too much details, the crucial words here are the quantum Kramers-Rao bound. Okay, so there's like a fundamental theorem that basically tells you for this mode of sensing, and again, assuming that the way I imprint the parameter of interest is 1 qubit at a time, if you don't have entanglement, your sensitivity, your estimation error will always grow, or at best grow, is 1 over square root of the number of qubits. If you have the right type of entanglement, and here in this quantum circuit, this green blob is supposed to be entangling our qubits, things can grow as 1 over n. Okay, so the big question is, how do I get the right kind of states that give me this 1 over n scaling? What are ways of preparing those states and using them that are robust against all the terrible things that are trying to degrade our quantum sensor? Okay, one more just piece of what do we formally calculate, right? How do I know? You come to me with some state, you're like, oh, I think this is a really good state. How do I know it's a good state or not? There's this quantity that we call the quantum Fisher information that really answers the question at some fundamental level. Is your state going to be good for this kind of sensing or not? And again, what is the sensing? You started with some state, and then you apply this perturbation that depends on the parameter. You now have a new state that depends on theta. Is your initial state a good state or not? How different are those two states? So this quantity, the quantum Fisher information, really just look at this first term. If I imagine taking the derivative of this state with respect to theta, this quantum Fisher information is basically telling me how big is that quantity, right? And again, if you don't have entanglement, that has to grow like n at best. If you have the right kind of entangled state, you can get an n squared scaling. Okay, and again, then the quantum Kramers-Rao bound tells us this Fisher information, which is just a function of your sensing state, that directly bounds the best sensitivity that you can possibly estimate this parameter theta with. Okay, so we're looking for states that have the right kind of entanglement that gives me the best possible quantum Fisher information. Everyone good? Cool. Okay, so let's try to connect to the story that I want to tell you about. So here is our general sequence of things that we have to do for sensing. The first thing we have to start with, if we want to do quantum sensing, is I need to have the right kind of entangled probe state. Okay, I'm going to focus on the setting of this Ramsey-style sensing protocol, right? And again, I told you about these spin squeeze states. They do involve a kind of entanglement. This might not look entangled to you. I will tell you what kind of entanglement we have in just a bit. How do I prepare this? Again, I already told you the standard way of doing it is design some good Hamiltonian that will evolve an unentangled state into this useful entangled state. Okay, the most common way of doing it is put all your two-level atoms or your qubits into a cavity, use the photons in the cavity to generate some spin-spin interactions. The most common kind of interaction is this thing here. This is, it's an all-to-all ZZ interaction. So every qubit interacts with every other qubit with a classical Ising interaction, this ZZ interaction. So this is called a one-axis twisting Hamiltonian. If you really want to know why, I can explain that to you. It's been realized in all sorts of experiments. It is maybe one of the two most popular ways of generating spin squeeze states in modern cavity QED experiments in AMO physics. It's great, it's ubiquitous. If I wanted to be picky, what's a problem with this approach? Well, first of all, this is a purely unitary protocol. If I add dissipation to this cartoon, this thing is not that robust, right? The spin squeezing can be degraded. And also, if you just use this to generate spin squeezing, and again, what was my goal? My goal was to get this beautiful 1/n² scaling. This will never give you that. Okay, so it's not able to reach what we call the Heisenberg limit for this kind of estimation. Okay, so the first thing I want to tell you about, what is another way to get spin squeezing that maybe doesn't even involve a Hamiltonian, right? That uses some kind of controlled dissipation. And then once I tell you that, is this just some theorist playing games, or can someone actually build this, right? Okay, and again, what's the dream with the dissipative protocol? We know that dissipation can be used to prepare states. So imagine I have a collection of qubits, I couple them to some zero temperature environment. Think of that as a fridge. So the qubits, maybe some of them start in their excited state, some of them don't. Eventually, all the qubits will decay, dump their energy into this fridge. No matter what state you start with, you'll end up in this kind of maybe boring state where all the qubits are in the ground state. Okay, so we want a more interesting fridge, right? Where there's some crazy non-equilibrium environment. And spoiler alert, that's going to be some kind of cleverly driven cavity. That non-equilibrium environment does the same thing. No matter what state you start with, it relaxes you into some final pure state. But I want that final pure state to be something entangled in a way that's useful for metrology. Okay, and so this is easy to draw in PowerPoint like this. How do I actually construct some dynamics like this? Okay, and again, what I'm going to do is go back to something simpler than a collection of n qubits. Let's go back to a single harmonic oscillator. So a single mode state of light. And let's think about squeezing in maybe a way you're not used to thinking about squeezing. So this is the standard way of thinking about a squeeze state of light, just a single mode. I have this ground state vacuum noise distribution. In a squeeze state, I turn that into ellipse. There's this skinny direction that has been shrunk compared to the vacuum noise by this exponential factor. Okay, and if you've taken maybe Kanu's quantum optics class, you know that there's this squeezing operator, right? There's a unitary that will do that, right? So squeezing, we normally think about in phase space, because look, it's really easy. You're just squishing this thing. Let me do something different. Let's think about squeezing not in phase space, but in terms of photons in Fock space, right? So this squeeze state is some pure state of light. I could expand it in Fock state, so states of definite photon number. And when you do that, you find something really nice, right? Let's not even worry about these coefficients, right? Part of it depends on the squeezing parameter. But you see in this, writing the squeeze state in the Fock bases, I only have even integers here. Okay, so the thing I'm going to use, because I want to generalize this to think about spin systems. If I think about a squeeze state in Fock space in terms of photon numbers, it only has even photon numbers. Okay, so that's pretty unique. So it's not a ground state. It has excitations in it, but they only come in pairs, right? So there's this pairing structure. So what's another way of thinking about a pairing, kind of a state that has pairing correlations? Well, I could define this state by what kills it, right? So what's the ground state of a harmonic oscillator? It's the state that's annihilated by the lowering operator. So this crazy squeeze state that has these superpositions of even photon numbers, it's also annihilated by some fairly simple operator. But this operator now is a combination of just our ordinary photon lowering operator and a photon raising operator. And the coefficients here, this caution R, are directly related to the amount of squeezing. Okay, so a weird, maybe not, depending on who you are, weird way of thinking about a squeeze state. A squeeze state is a state with these pairing correlations. A squeeze state is something that's not annihilated just by a lowering operator. I need exactly the right combination of lowering and raising operators. Okay, so this is a structure that comes up all the time, for example, in condensed matter physics. I could just call all this stuff in the brackets. Let's call that some new operator. I'll call it beta. Beta B is for Bogoliubov, right? I'll call this some Bogoliubov mode. So whatever this squeeze state is, it's annihilated by this thing beta. So now what is nice, right? I want some dissipative dynamics that will prepare this squeeze state. If I just wanted to prepare the ground state, right, of a harmonic oscillator, we know how to do that. You need a zero temperature fridge. How do you get a zero temperature fridge if the only thing in your lab is a lossy cavity? Well, you could play some version of cavity cooling. Okay, so the whole trick is for getting a squeeze state using dissipation, again, just for bosons to begin with, I am going to do a version of cavity cooling. But what am I going to cool? I'm not going to cool to the ground state. I'm not going to remove excitations of the photon raising operator. I'm going to cool to this ground state. I'm going to remove excitations from this beta mode. Okay? And so just a cartoon version of how to describe this. So now my cavity is described by a lowering operator and a raising operator C and C dagger. I've depicted the thing I want to squeeze as a mechanical resonator. It has a phonon lowering operator B. This cavity is lossy. So the cavity has some loss rate kappa. Okay, so here's an interaction that's allowed. So I can create a photon in the cavity either by removing an excitation or creating an excitation in the mechanical mode, right? Exactly paralleling the structure in this Bogoliubov mode. And what's the cartoon picture? The cartoon picture is when this Hamiltonian acts, right? I can create a photon in the cavity and it's going to rapidly disappear. And then that can happen again. Okay, so my cartoon picture of the dynamics is I turn on the dynamics, right? If psi is the initial state of this mechanical resonator, when a photon leaves, right, it had to be produced somehow. I basically acted on the mechanical resonator with the stuff in the brackets with this beta. And then what happens? Another photon leaves, I act again, right? And again, right? So this is the picture of the dissipative dynamics. This stuff here is creating excitations in the cavity. The photon leaves, it repeats. Every time a photon is emitted, you've acted with this combination of operators on your mechanical mode. Okay, and this interaction might seem pretty simple, right? You just convert one excitation to another excitation. This thing seems a bit weird, like a C dagger, B dagger. That means there's something I'm not drawing in this cartoon. There's some external energy source, right? Think about some three-wave mixing Hamiltonian that's giving rise to that term. Okay, but the crucial thing for us is, okay, if you have this dynamics, what happens if I keep going? Well, it's just like cooling. You eventually run out of betas to remove, right? You eventually reach a state in the mechanical mode where you can't remove any betas, and then you're stuck. Okay, so the cartoon is you basically end up in a steady state, right? No matter what state you started in, that is exactly this squeeze state that we want. Okay, and so that's a cartoon. I'm not going to dwell on it. There's a way to turn that cartoon dynamics into a completely legitimate dissipative quantum evolution equation. So this would be the equation of motion for the density matrix of, in this case, the mechanical mode. There's a bunch of stuff on the right-hand side. Unless you're one of Kano's students, you don't need to know what that bunch of stuff on the right-hand side is. The only thing you need to know is the operator you're trying to cool, in this case, this Bogoliubov mode, is sitting there. Okay, so at a cartoon level, this is a way of generating some dissipative dynamics that will take some arbitrary initial state and stabilize this nice bosonic single mode squeeze state. Okay, and again, because it's not the main thing I want to talk about here, this is sort of an old idea. There are by now a number of different experiments that have implemented this basic cooling to a squeeze state protocol in optomechanics, in trapped ions, in superconducting circuits. But I want to do something more complicated, right? I want to go back to those spins, right? And I want to produce this spin squeeze state, right? I want the spins to somehow be entangled and squeezed. And so the question is, like, you know, let's play the lazy theorist hat. Let's just try to copy exactly what works so simply and beautifully for our single harmonic oscillator. So what did I have to do to, and again, this is the kind of thing that I'm after. What did I have to do in the bosonic case? I needed to cool this combination of a lowering and a raising operator. Well, I know how to write down a combination of raising and lowering operators for spins, right? So now again, my spin ensemble, think of it as large collective angular momentum. I have collective, lowering, and raising operators. I could again say, oh, let me take some linear combination of lowering and raising, exactly like I did with bosons, and ask, is there some state that is annihilated by that? Is that state a squeeze state? If it is, I could play the same tricks to cool this that I did to cool that, bosonic Bogoliubov mode. And of course, what's the problem? This is all great to just say, hey, look, that looks like it's going to work. The problem is sort of an obvious one. A is not the same as S minus, right? A bunch of spins in general is not the same as a harmonic oscillator, right? When I have a collection of n qubits, they have a finite Hilbert space. They don't have the infinite dimensional Hilbert space of a bosonic mode. To really get a lot of squeezing, I'm going to need to use all of my Hilbert space of the spins. I can't just pretend that what worked for bosons will work for spins, right? So the question is, hey, I could try this theoretically and see, does it actually lead to something good? Okay, and what's the answer? Does this work? Does it not work? The answer is it both works and it doesn't work, right? So that is, it does work in a way that's really useful to us, but there's some nice surprises that come from the fact that we now have spins and we don't have harmonic oscillators. Okay, so now here is my cartoon. I've got a bunch of spins in a cavity. The cavity is lossy. The spins are going to interact with the cavity, maybe helped by some drive, in the same way that I did things with the boson. So C are photons in the cavity. To create a cavity photon, I can either remove an excitation from the spin ensemble or create one. Okay, and there's two coefficients there. That will lead to this nice linear combination of spin lowering and spin raising, determining my dynamics. Okay, so the first thing that's kind of cool is that this dynamics, this dissipative evolution, this is actually something that was in the literature a long time ago. If you were lucky enough to have completely broadband ideal squeezed light and you shone that light on a bunch of two-level atoms, this would be the dissipative dynamic. So this cartoon is trying to indicate if you realize this dynamics, you're tricking your spins into thinking they've been exposed to strongly broadband multimode squeezed light. Okay, but the idea is you've just tricked the spins into thinking that. To implement these ideas, you don't need any non-classical light at all. Okay, and the question is, does this work? Because I was trying to tell you spins are not the same as bosons, right? So there are kind of many surprises here. Let me just tell you one. So this is showing the amount of squeezing in the steady state. If you run this dynamics and just wait, how squeezed are you? This is the squeezing parameter, right? So if R is 0, this term isn't here, that's really boring, right? There's no squeezing. You're just relaxing the spin ensemble to have all the qubits in the ground state. As you turn up R, you're turning up the squeezing, right? And again, anything below 0 here, this is in dB, you're doing better than this standard quantum limit scaling. Okay, and then this line here, this is for 200 spins. This is this Heisenberg limit where your sensitivity doesn't go like 1 over root n, it goes like 1 over n. So what is this curve showing? Well, hey, look, things are getting better, better, better. And the solid blue curve, you can really get Heisenberg limited squeezing. Okay, so that's already kind of cool because this standard Hamiltonian way of doing things does not, in the simplest way, give you Heisenberg limited squeezing. But then what about this crazy blue dashed curve, right? It follows this curve initially, and then something terrible happens, right? You actually have more noise than you would have in a product state. So the crazy thing that happens with spins that does not happen with bosons is that you have a very, very strong even odd effect. So whether you have 200 atoms or 201, whether you have 10,000 atoms or 10,001, if you make this R parameter big enough, you have a macroscopic sensitivity to the parity, right, of the total number of atoms. Okay, so again, if you're trying to use this for measurements, this is a really, at first glance, a bad thing. You don't panic, you just work out here where you can't tell the difference. But maybe if you're interested in the basic physics, or maybe for some reason you care about watching atoms leave one by one, this regime is potentially super interesting. Just to give you a flavor of why on earth would something like this occur, right? I told you that these squeeze states, if you go ahead, kind of, yeah.
Red dash.
So the red dash curve is the purity, and that's showing the purity in the case where I have an odd number of spins. So the idea is that when you make this R parameter very large, if you have an even number of spins, you get lots of squeezing, you have a pure state, so the final state has no entropy. This blue dash curve, which is 201 spins, not only is the squeezing getting bad, you don't have a pure state, okay? So you have some entropy, there's a mixed state that you're generating, okay? Yeah.
What is that sort of breakover point? What does that actually sort of, in terms of R?
It's sort of the limit where it's the amount of squeezing you would need naively to get something close to Heisenberg level squeezing. So this e to the 2r parameter is roughly order n. So this breakdown point will become larger and larger as you have more and more spins. And I can give you like a cartoon that gives some sense of what's going on. So I told you with bosons, these squeeze states, they're paired. They only have even numbers of photons. If you have a very, very weak squeeze state, it's like a superposition of like 0 and 2. If you have a lot of squeezing, you have lots of excitations. So what's the problem with spins? So with spins, I can do the same thing. I could write my purported spin squeeze state as a superposition of Sz eigenstates, right? So if Sz has its minimum value minus J, that's all the spins that are down. So these spin squeeze states, these blobs are supposed to represent these amplitudes alpha J. So these spin squeeze states also only have amplitudes for even numbers of excitations, okay? And the idea is to get a state that is annihilated by these operators, I need every odd number of excitation state to be sandwiched between two even numbers of excitations. So what's the problem? If I have an odd number of spins, there's always going to be something left over, either at the top or at the bottom. Okay, so we want a paired state. I want this kind of perfect pairing where the bottom state and the topmost state are definitely paired. If I have an odd number of spins, there's just no way of doing that. Okay, and if you don't squeeze very hard, you kind of live down here, you don't see that. If you start to squeeze pretty hard, that really becomes a limitation. Okay, so this is just like one kind of surprise that comes out in this kind of dissipative spin squeezing. I won't belabor this. One of the hopes is if you prepare these interesting states using dissipation, maybe if there's bad dissipation, you'll be more robust. That sounds great as like a thing to say. Is that actually true? Here's one example where now we're saying, okay, we don't live in a world of perfect experiments, right? Our qubits are not perfect. Maybe our qubits have just ordinary, spontaneous emission. Maybe our qubits have T1 decay. So each qubit by itself will decay independently from excited to ground at some rate. Okay, and the question is, how much squeezing do I get? How is that limited? By the fact that I have this kind of decay. Okay, and what this is showing is I'm holding the strength of the T1 relaxation rate fixed. Because these effects, both the spin squeezing, the dissipative scheme I told you about, and even this Hamiltonian I introduced first, they're all collective. They all get better and better, even fighting this bad dissipation, the more spins you have. But the point I want to make here is, this is the unitary approach. This is the dissipative approach I told you. This is an example where the dissipative approach is giving you an advantage, right? The orange curve is below the blue curve. Even the power law is a little bit better. Okay, so there are other advantages as well. These dissipative mechanisms can give you more resilience to bad dissipation. Just really quick, a little bit about turning this kind of cartoon into something real. Right? I would love to tell you that We've been working with experimentalists, and they've realized this dissipative spin squeezing. As far as I know, no one has done this even in a very, very pristine atomic cavity QED experiment. I think it's definitely doable. We've been working with some even more ambitious experimentalists. We've been working with experimentalists that want to generate spin squeezing, not using pristine two-level atoms, but using kind of messy, dirty ensembles of solid state spins, right? So for example, NV defect centers in diamond, these defects that can act like optically addressable qubits, these are things that are already known to be practically useful sensors. If you could spin squeeze them and improve sensitivity, maybe there are immediate sort of practical ramifications. So in terms of realizing the kind of ingredients to get this dissipative physics, we've been working with Anya Blazinski-Jayic's group at UCSB to do something ambitious. The spins here, these defects in diamond, they're embedded in a diamond optomechanical crystal. Okay, so this is like a patterned beam of diamond, this pattern of holes. There's a defect here that you can barely see. In the diamond, you have both a localized optical mode and acoustic mode. Those ingredients together can play the role of the cavity here. So there's a way of realizing this kind of dynamics in this system where it's the spins talking to a mechanical degree of freedom that ultimately will act like the squeezed ingredient. There's also really nice ways of doing this in superconducting circuits. In superconducting circuits, you can get a lot of nonlinearity for free using Josephson junctions. People have already done the dissipative squeezing of just microwave photons in a cavity. People have coupled microwave cavities to spins, right? Why not put those things together? Okay, so I'm obviously going much slower than expected. I have about 10 minutes. Is that good? Okay, so let me give you a flavor that I started with something really grand. I said, oh, dissipation is great for quantum sensing. And it'd be a bit disappointing if I just gave you one example, right? Oh, there's one thing we can do. I'm not going to have time to do this justice, but what I just told you kind of scratches the surface of a whole bunch of interesting dissipative protocols for getting many body entangled states that are useful for sensing. And one of the exciting things, what I just told you about was kind of getting a state we already knew about. We knew about spin squeezing, we knew ways of getting it. This was a different way of getting it. The cool thing is thinking about these dissipative protocols also lets us realize new kinds of entangled states that maybe we didn't know about before. Okay, so what I'm showing you here is a situation where, let's be greedy, if one spin ensemble is good for sensing, what if I have two spin ensembles, right? And what if they're a little bit spatially separated? Okay, here's my cartoon, and for some reason there's not a lot of spins in each ensemble, but imagine there's lots of spins in this guy and this guy. So now you can imagine new possibilities. Well, now I could imagine doing differential sensing. So maybe I have a magnetic field that varies in space. I want to know the gradient, how the X magnetic field changes, how the Y magnetic field changes. Maybe I want to know about those gradients and not be sensitive to common node fluctuations, right? Do you have an entangled state for me? Is there a way to entangle these ensembles in a way to do this kind of sensing optimally, get this kind of Heisenberg limit? Okay, and again, time is running short. You know, at some point you run out of ideas, so you just use the same idea over and over. And the idea is, well, look, if it works for bosons, it's probably going to work for spins, right? So if I have two harmonic oscillators, many of us also know about two-mode squeeze states, right? So if I have these two harmonic oscillators, each has an X and a P quadrature, I can think about a kind of squeezing where I haven't drawn the phase space, but I reduce fluctuations in these two composite quadratures. So the sum of the X's, the difference of the P's. So that two-mode squeeze state, you know, one of the basic resources in, you know, continuous variable quantum information. Again, you can ask, what does that look like in Fock space? So again, these are states of definite photon number in oscillator 1 or oscillator 2. There's again a kind of perfect pairing, right? I only have states where the photon numbers match in both modes. Okay, and now notice the coefficients are much simpler. You can again play the same game and say, well, look, this kind of correlated structure here, I can encode that in operators. So this two-mode squeeze state, there's two modes. There's two of these Bogoliubov modes. So now this two-mode squeeze state is the vacuum of two operators. Each is a combination of destroy a photon or a phonon, create one. But one is for mode one is for mode two, right? The other one is just exchange those two indices. Okay, so this is standard physics of two-mode squeeze states. The question is, does this now, can this be generalized to two-spin ensembles? Okay, and the surprising thing here is, the answer is yes. And the answer is two-mode bosonic squeezing generalizes in a way that's much more universal than single-mode squeezing. Right, so this is without the normalization factor. This is my bosonic two-mode squeeze state. I sum to infinity. If these are now two spin ensembles where I have n spins in each ensemble, this is going to be my working definition of a two-mode spin squeeze state. These m tilde states, these are just different numbers of excitations in each ensemble. And all I've done is I've just truncated it, right? I just said, well, look, you can't have infinite number of excitations. Don't change the coefficients, right? Just truncate that. And at first you're like, how is this ever going to be relevant to the spin system? But it is. If I just play the same tricks, I turn these bosonic lowering operators into spin lowering operators, S1 minus, S2 plus. This state with no funny coefficients out front is the vacuum of this, let's call it a spin Bogoliubov mode, and the same one with two exchange to one. Okay, and also this state has all sorts of remarkable sensing properties. So it lets you measure these differential fields with Heisenberg limited sensitivity. It gives you a way of sensing in a way that's completely immune to common mode noise. It's just a wonderful state, right? And this is, someone really likes the state, I guess, right? It's a kind of an amazing sensing state. It's one that wasn't really known, to the best of my knowledge, just by studying unitary protocols.
Does this have the same even odd thing?
It does not, because the nature of the pairing now, right, this, whether this is even or odd doesn't matter. Because now the kind of correlations are between the ensembles. It's not about correlations between different even Fock state numbers in the same ensemble. Yeah. I won't belabor it, but the cool thing is you come to me with some arbitrary bipartite system. Who knows what it is? There's two systems. There's some finite dimensional Hilbert space for each of them. There's some lowering operator for each system, some raising operator. You don't tell me what those coefficients are even, right? They could be anything. This trick just always works. So the fact that this kind of dissipation, this generalized Bogoliubov operator, and you're not telling me what these coefficients are, this will always stabilize this kind of state. Okay, and again, it does not work like this in the single mode spin squeezing case. The coefficients in the state look very, very different. This is just much more universal. So the exciting thing here is thinking about these dissipative protocols. There's even the possibility of completely new kinds of sensing states where you pick your favorite two systems, you pick your favorite version of a raising and a lowering operator. Maybe it's even like A squared is your O, right? Maybe you're talking about states where you raise excitations by 2. There's an interesting state that enables Heisenberg limited sensing. Okay, so time is rapidly dwindling. You can even go crazier. And here I'm just going to show cartoons, but I've told you about one ensemble. I've told you about 2 ensembles. What about many ensembles, right? So this is using some different physics, no Bogoliubov modes. This is a setup that Kanu, among others, kind of, I think, loves, right? This is the kind of setup you would use to study collective spin physics in AMO physics. I've just got a bunch of atoms sitting in a cavity. Maybe I drive the atoms, and they all decay collectively through this lossy mirror in the cavity. So the idea is we don't want collective states. I want my different spins to be different. If I now have different detunings of the drives on different groups of spins, so I break these into little sub-ensembles. So this is the drive on each sub-ensemble. This is a detuning. I need some kind of collective interaction that's mediated by the cavity. The amazing thing is this dynamics combined with just this collective loss through the cavity, you can stabilize all sorts of interesting entangled states. Some of these entangled states are really amazing for sensing. So you can do this with 4 ensembles, get a kind of entangled state that can let you measure not just gradients, but curvature. Okay, so I know the details here probably don't make a ton of sense. I want to give you the impression that this idea of using dissipation as a resource, it's not a one-hit wonder. There really does seem to be a huge number of possible ways of preparing states we already care about, but also discovering new sorts of entangled states that are useful for metrology. Okay, so I think I am at the end of time, so I'm just gonna flash through this. You can bug me about it later. Put up my conclusions. Hopefully I've given you a flavor of kind of our work in this direction, why we think dissipation is kind of a cool way to sort of approach metrology. I will stop here and yeah, thank you for your time.
Beautiful, Ash. Questions?
So about the surprises, this even odd
Yeah,
feels really strange.
I'm glad you say that because there's some people who will tell me, oh, this is completely obvious, and then they'll give me an explanation. But
So,
yeah.
I understand that you obtain it with the ideal dissipative dynamics.
Yeah.
And so if I understand what you said, then this break-off point moves further and further as you increase the number of partners. What happens if this dynamics that you impose is not just totally perfect? You know, it seems to me very improbable that you could design a measurement which would tell you, is there an even or odd number of electrons in the universe? Because that's what you are saying.
But with the caveat that you're able to generate this kind of dynamics with enough precision, right? So that's, I think, kind of at the question you're getting at, right?
Right.
Yeah.
So, yeah, is it sensitive to how precise this dynamics is?
Yeah. So there is, so the question is like, what if I perturb this dynamics by adding extra terms here that look, for example, we know in an experiment. I gave an example. I said, well, look, in reality, there's other dissipative dynamics. Each spin could just decay from excited state to ground state on its own. So if that dynamics is strong enough, that will definitely wash away this difference. It will kill this physics. How strong does the good dynamics have to be compared to the bad dynamics? It's like many kind of collective effects in cavity QED. It boils down to a collective cooperativity parameter being large enough. There's another, I think in the vein of your question, important consideration. I told you that you get these states as dissipative steady states. You turn on this dynamics, you wait, you get this state. I didn't tell you how long you have to wait, right? So that's another kind of concern. If the time scale for getting this goes off to infinity, you'll never see this. When you put in the bad dissipation is saying you don't have forever, right? The bad stuff will kick in and limit you. So in our paper on this, we have like a more worked up proposal for doing this in a trapped ion setup. We put in realistic heating rates. And again, we didn't have 200 trapped ions. I forget if we did it for like a dozen. It wasn't completely unrealistic to sort of see this physics, right? The thing that we were really curious about, and we still don't have a great answer, is there ever a regime where this would be an interesting sensing modality? So now the signal of every time you lose an atom from your trap, for example, would be the fluctuations of the ones that are left would kind of change dramatically. And often we don't like the noise being the signal, but I feel like that's still something to think about a bit more. Yeah.
So for this Colloquium operator, how critical is it to get the coefficients of the raising and lowering operator just right?
Oh, so okay, I could always rewrite this. I could just like take this cosh out of here. So I have an S minus, and then I have an S plus, and the crucial thing is how big is the coefficient of the S plus compared to the S minus? Okay, so as long as you have both of those, you're going to get some version of this physics, right? The tricky thing is I want to be out here. What does that mean for R to be really large? These things are almost perfectly balanced, but not quite, right? If these were perfectly balanced, that's not good because this becomes a Hermitian operator. This becomes like Sx. I want to be really, really close to that, but not there. So experimentally, experimentally, you're not going to be out here in a first experiment. Experimentally, the trick is to get both of these processes to interfere, right? So you want, really easy to write down as a theorist, an interaction where when I produce a cavity photon and it leaves, I don't know if I did that by acting with S minus or I did that by acting with S plus. Okay, and anything that gives you, let's call it a kind of which path information, that which process generated that outgoing photon, that will disrupt this physics because that will give you some independent, let's call it cooling with an S minus and independent heating, right? But again, that's something that, we believe is it's something that you can realize in a bunch of different experimental protocols. And again, this idea, it hasn't been done with spins, it has been done with bosonic degrees of freedom. So motional degrees of freedom in trapped ions and optomechanics, and the squeezing of like an intracavity microwave field with superconducting circuits. So we think the interference is something that's doable, but you always learn things by doing an experiment. It would be great to see someone do an experiment in the spin case.
Would measurement and feedback here, how would that change or speed up the process?
Yeah, that's an interesting, and I feel like there are some papers that have looked at this. So there's a completely different way of generating squeezing, which is just doing measurements, right? If I measure one quadrature really well, I get to know it super well, and then I have squeezing, it's conditional. If I do feedback, I could turn that into squeezing someone could use, even if they don't have the measurement record. So there's an interesting question of like combining this kind of dissipative squeezing with measurement-based squeezing, right? And I feel like there's some papers on that. I feel in principle you can do a little bit better, but the complexity of the experiment kind of grows. We become very interested in just if you do realize this, but now you look at the photons that are emitted out here, that enables all sorts of new sensing modalities. And so that's something we're pretty excited about and is, again, something unique to these dissipative approaches. Yeah.
So very nice talk, first of all, very interesting images. How do you think this could apply to something like, say, neutron spins? Is there a way in which you can still have this sort of dissipation when you have a system that's perhaps less sensitive than an atomic system?
Yeah, I think that so you still need the kind of controllable couplings, and I guess that's the thing that, like the kind of coupling I'm drawing here, right? We know how to do that in a lot of different physical platforms where we have a lot of control over the constituent degrees of freedom. That's an interesting question. Like, yeah, off the top of my head, I don't see some obviously simple way of doing it with, like with other degrees of freedom. But it's an interesting thing to think about. Yeah. Yeah. Yeah.
This part where you showed the bifurcation between even and non squeezing in the regime when you're still below like the 0 dB squeezing, but you're on the odd pad, is that actually like a signature of like squeezing and the conjugate observable?
So when you're right. So when I don't pick this R too large, I'm kind of modest in what I want. Both the 201 and 200 spins, they follow the same curve, and both of them are giving you spin squeezing that, again, it's below 0, so you're getting useful spin squeezing. So, and again, the cartoon was, if I don't try to squeeze too hard, I never see the bounds of Hilbert space. And so I can't tell if I have 200 or 201 spins. And so here, the squeezing would always be in the same direction. I think the way I've drawn it here, it's in the x direction. So the fluctuations in the collective SX variable of these qubits, in both cases, right? So this is like something like, 10 dB, what you would have in a product state. So out here, and that's, I guess, important that out here, you don't have to control the parity of the number of spins in your ensemble to get something useful. But the squeezing here, you've cooked up the dynamics to pick a particular direction. It's always the same direction that ends up getting squeezed. If you wanted to change that, you'd have to change, if you want, signs in the coefficients there.
I guess has drastically reduced squeezing. It's not like you're squeezing at a different quadrant.
No. And I think Kanu asked about this. A way of seeing what's going on is this red curve is telling me what's the purity of this state. Is it still a pure quantum state? Now, pure quantum state would be, if things get fat in one direction in phase space, they get squished in the other. If I have an impure state, it could just be like a thermal state where there's like more noise everywhere. And this is sort of telling you that that's actually what's happening, right? You're getting a lot of fluctuations in like all directions. It means it's no longer a pure state. So I think there, like, if you want to think of that state as somehow being useful, I think it's useful in the sense that it's very different than this state, right? And so maybe that's something you could harness for some particular sensing target.
I'm trying to understand where the magic comes in.
Yeah.
Because it seems to me that you are creating kind of a sophisticated state, which will be good for usage because it's complicated and will be sensitive to zillion things. Is it correct to say that you put in the magic at the beginning because you design your dynamics as very specific and, as I said before, ideal? Is it okay to say that maybe there is some other combinations, and as long as I am able to proceed with this evolution very, very nicely, like ideally, then I will get states that will be useful.
Yeah, so I think you're hinting at like a really, really important question. And there's two parts to the question. One is, okay, imagine I prepared this state perfectly. Give me that, right? Now I want to use it, right? And now there's a question of, can I use it in a way where I get this promised sensitivity, or in the act of using this state, and like I talked about like a rotation of the collective spin, if bad things are happening while I'm using the state, then there's a competition that I'm trying to acquire this signal and keep the noise low, but all this bad stuff is happening. And maybe the bad stuff is accelerated by the fact that I tried to be clever, right? And there is a no-go theorem that basically tells you if you just do things in the most straightforward way, if your spins are really limited by Markovian noise, you can never get this Heisenberg limit type scaling. You will end up at most doing, I'm forgetting what the factor is, like something like a factor of 2, better than just having a product state. So there's one issue in terms of using the state. And then again, I have to be clever. Maybe the noise is non-Markovian, right? Maybe I can do some kind of error correction. There's all sorts of tricks there. The other part of the question you were asking is like, in the dynamics of trying to prepare this entangled state, what happens when I add other bad dynamics? And like, there's an infinite way to add bad dynamics. This plot was an example of one common thing you might have to worry about. So while I'm trying to prepare the state with this dissipative dynamics, I have T1 decay. Each spin can individually relax at some rate 1 over T1. So that also will limit the amount of squeezing you're getting. The power laws here are not the same as what I had in the ideal case. But the squeezing here is all negative. You're still doing better than a product state. And things get better the more spins you have. Okay, and that's the, there's no theorem about this, but the hope is this kind of resilience is better when you do things in a dissipative way than when you do things in a unitary way. It's like good dissipation fights bad dissipation better than unitary dynamics fights bad dissipation. Overstatement and oversimplification, but that's the hope, right?